The purpose behind this lab was to apply our knowledge of curving motion principles, parallel and perpendicular components of force, Newton's second law, F net equals dp dt, and the universal gravitation formula, Fg equals negative gmm over magnitude r squared times r hat, to collect data from a computer model of an orbiting system in order to estimate the mass of a black hole at its center, as well as create a model of a rocket ship's path through a planetary system. Summary of the results. The data collected for the mass of the black hole fluctuated in value, indicating slight inaccuracy in the model of the system. The path of the rocket through the planetary system was not a perfect figure-8 flight pattern. Trial and error only resulted in having the rocket make 2 loops around the planet and moon. Black hole and star orbiting system. The system is a star with mass 2.0 times 10 to the 30 kilograms and radius 3 times 10 to the 11th meters. The source is a black hole with unknown mass m that we will solve for, and a radius r equals 3 times 10 to the 11 meters as well. We had to fill out the code to solve for the momentum, change in velocity, and FNet, as well as the parallel and perpendicular components of FNet. We used many principles like P equals mv and the parallel direction of force and magnitude of force. F net parallel equals b hat times d magnitude parallel over dt, and that F net perpendicular is equal to the F net minus the F net parallel. We use this to calculate the mass of our black hole using the universal gravitation formula. We'll explain that on the next slide. Derivation for solving for our mass of the black hole. As you can see, we took the magnitude of each side and then solved for big N. We gave a value for the black hole's mass at every step of the calculation loop. So we took the average of all of these values because there was almost 500 values. The result ended up being mass equals 1.11 times 10 to the 34 kilograms. As you can see on the right, there's a chart of all of the values for each step. Previously stated, the black hole's mass was calculated to be around 1.11 times 10 to the 34 kilograms. The graph showed how that there were slight deviations in the value of the mass per calculation loop. These could be caused by a combination of things. The most likely culprit is a large value for delta t. This means that the result of the FNet calculations for each position are very different from one to the next. Reducing delta t would make the values more accurate. Another reason is issues with the model being slightly inaccurate with representations of the data, which isn't anybody's fault, because numbers can only be stored so accurately in a computer. While FNet and the change in momentum are equivalent mathematically, they aren't necessarily equivalent in their meaning and concept. FNet perpendicular and parallel are simply the net forces applied in the perpendicular or parallel directions, a summation of all the forces in a respective direction. Whereas the change in momentum deals directly with the object's motion. It measures a change in direction or speed. The change in perpendicular momentum deals with a change in direction, having no effect on the speed of the object. dp perpendicular over dt equals magnitude p times dp hat over dt, or the change in p hat over change time. Whereas the change in parallel momentum deals directly with the object's speed. It changes the magnitude of the speed. dp parallel over dt equals p hat times the change in momentum over dt. Spaceship traveling through planetary system. Spherical spaceship with mass m equals 7 times 10 to the 12 kilograms and radius r equals 1 times 10 to the 7 meters, and starting on the surface of the moon. The sources are a moon with mass m equals 6 times 10 to the 25 kilograms and radius 2 times 10 to the 7th kilograms, or meters, and a planet with mass m equals 8 times 10 to the 27 kilograms and radius 4 times 10 to the 7 meters. To calculate the r vector from the planet to the moon, the ship to the moon, the planet to the ship, and the moon to the ship, as well as the force for each of those respectively. And then in total, we found the FNet on the moon and the FNet on the ship, which we used to plug into the position and velocity update formulas for both the moon and the ship, because the planet is stationary. Using this, we created a model of the ship's path around the orbiting moon. The ship's path through a perfect vacuum, being affected by a planet and a moon. It was beyond the scope of this lab to try and calculate the perfect x and y velocities for the ship to create a perfect figure-8 orbit, so we guessed and checked until we reached values at x velocity equals 7976 meters per second and y velocity equals 41110 meters per second. This is what the model looked like. In order to create a model with a black hole, a star, a planet, and a moon, and a ship, you would need to calculate the force applied by each object onto each object. Essentially, treat one object as the source, and treat every other object as a system for each thing respectively. Then apply the position and velocity update formulas for each object. This would be incredibly time-consuming, but it'd create a model for the system. The most dominant interaction of the system would be with the black hole, given it's the most massive and would put the largest magnitude of force upon each object, even if individually some objects may have more forces acting upon them at a greater magnitude.